In this video on rational exponents, we will use the following properties to simplify. When you multiply like bases, you add exponents. When you divide like bases, you subtract exponents, and negative exponents, you reciprocate the base, and then the exponent becomes positive. We'll now use these examples to solve a variety of problems or to simplify. In our first example, we'll take y to the 3/4 and multiply it by y to the 1/6. So we have fractional or rational exponents. Multiplying like bases, you add exponents. I want to see what's coming. I notice a need to have common denominators between 4 and 6. Their least common denominator is 12. So I'll rewrite them. 3/4. To get the 4 to be a 12, I need to multiply by 3. So I do the same to the numerator to make 9/12. The other exponent of 1/6, I need to multiply its denominator by 2 to make it a 12. So I also multiply the numerator by 2 to get 2/12. And then simplifying, I get 11/12 as the exponent on y. So y to the 11/12 power is the final answer. In the next example, I'm going to divide q to the 5/8 by q to the 3/8. So when dividing like bases, I need to subtract exponents. I already have common denominators, so I operate on the numerators, keeping the denominators the same. And always simplify whenever possible. For the final answer of q, for the final answer is equal to q to the 1/4 power. So when you divide like bases, subtract exponents. What happens if in our problem we have a variable raised to a negative power? In this case we have x is equal to -1/3. The first thing is to simplify the negative exponent by reciprocating the base, so making it 1 over x to the now positive 1/3 power. But if you recall, raising something to the 1/3 power, say x to the 1/3, is the same as taking the cube root of that variable. So what we have on our hands is an irrational denominator. In the past, when we had an irrational denominator, we asked, how can we get the exponent to be the same as the index? And so we multiplied by something that would create an exact root. So we need 2 more x's multiplied together to achieve that goal. So then we would get the cube root of x squared all over now the cube root of x to the 3rd, noting that when you multiply like bases, you add exponents, so now we've created an exponent that's the same as our index. Creating an exact root, we finally simplify the cube root of x squared all over just x. Here, however, so you can always do the problem this way, but if you want to stick with the fact that you're starting off the problem with a fraction, we have another strategy that works as well. Here, creating an exact root is the same as creating an exponent of 1. So I basically have now the question, what do I multiply so that when I add to 1/3 it equals to 3 over 3, which is equal to 1 whole? And the answer is 2/3. So it's the missing part of the whole. So now I go ahead and multiply the denominator and the numerator by x to the 2/3 power. And so I get x to the 2/3 all over x to the 1/3 plus 2/3 power, multiplying like bases, add exponents. So I get x to the 2/3 all over x to the 3/3, finally for x to the 2/3 over x to the first, or just x. And if you start with a fraction or a rational exponent, then you must end with a rational exponent. In other words, if you convert and you took the process using the radical and your final answer was the cube root of x squared over x, you would have to rewrite using the fractional exponent. That's what you will most likely see as your choice if it was a multiple choice question. So there's a shortcut for this kind of problem. These are all your steps, but if, let's say, we have an example where it is, like, let's use the same example. So I know that I need, with the negative exponent, to put the term on the bottom, then with a positive power. And I know that the missing piece to make it a whole is 2/3. So what I could do is write that as the power of the variable in the numerator, and then just make it one whole in the denominator, so to the power of 1. And that would be the shortcut. So let me do that shortcut one more time with a different example, just very quickly. If I had, say, y to the negative 3/5 power, with the negative exponent, I write it as 1 over y to the 3/5. And 3/5 plus what is equal to 5/5, a whole. The answer is 2/5. So that's going to be the power in the numerator all over y to the 5/5, or just y to the first power, which is just y. And that would be the shortcut. Alright, one more example on this topic before we visit how to simplify indices of radicals. We have 16 to the negative 1/4 power times 16 to the 9/4 power. Multiplying like bases, add exponents. They already have like bases, so I'll get 8/4, which simplifies to a square of 16 to 56. So there are several ways that you could go about this problem. You could take the 4th root right away, and in that case you would get 2 to the negative 1st power, the 4th root of the other 16, 2 to the 9th power, and then you get 2 to the 8th. That would be one way to go about it. I think this strategy is easier. So as the last segment of this video, I'm going to simplify with rational exponents indices of radicals. Because for something to be fully simplified, it has to have the smallest index possible. That's a new idea. So let's take a look at the following example, where we have the 6th root of 4x to the 4th. Now there are going to be some shortcuts I'll talk about, but let me go step by step, first by rewriting the 6th root as raising that radicand now as the base with the 1/6 power. Radicals are rational or fractional exponents. And now, by the product of powers property, I could take the 6th root of the 4 and the x to the 4th individually. And if I rewrite 4 as in prime factorized form, so 2 squared, I now see that when I raise an exponent to an exponent, I multiply them, And so now I could simplify down the denominators of my rational exponents, which this whole time is really simplifying down what the index is. So I'll show all the work here. Raising an exponent to an exponent, you multiply. Now I'll simplify. So I get 2 to the third times x to 2 to the third. And because they have the same denominator, I could do the reverse of the power product property. And I could siphon out that denominator. So I could raise it all to the 1/3 power. And because I start with a radical, I need to end with a radical. And notice, the point of that problem was to make the index smaller. And at the same time, we made a smaller radicand. Those two equal the same thing, but this answer is in simplified form. So there is a faster way to do this. So you could rewrite the 4 as 2 squared. And notice what happens is your index and then both of your exponents are even. So if you divide out their common factor of 2 and simplify, you get the cube root of 2x squared much quicker. That's a shortcut after you know the reason why that it works. We'll look at a couple more examples. Next example, we have the 6th root of 16 over the 6th root of 2. Now, by the power of quotient property, if you ever need to, you can unraise the numerator and denominator by the 6th root, so to speak, and combine the numerator and denominator again. In this case, that's useful because they share a common factor of 2. So we get just now the 6th root of 8. So that was a nice simplification. And you don't have to rewrite it like this. Once you recognize that if they have the same index, then you could just divide out right here and then get to that step. Well, from here, I'll go ahead and I'll show the long way, the technical reason for why the shortcut works, and then I'll do the shortcut. I will rewrite 8 as 2 cubed. You always want to rewrite as prime factorized form so that you could get exponents in the game. And then the 6th root is really the 1/6 power. Raising an exponent to an exponent, you multiply. So I'll kind of do a shortcut here, and I'll just go 3 into 6 twice. And notice I'm left with a 1/2 then. And that's really square root. If you start with a radical, you have to end with a radical. So the shortcut then would be to go over here, keep the 6th root in the problem, but rewrite 8 as 2 cubed, recognizing that the index of 6 and 3 share a common factor of 3. So you divide it out, and really the square root of something, you don't have to write the index of 2, and you get the answer all the same. So that covers that topic. And then a related topic with rational exponents is rationalizing a denominator using a conjugate pair. So this will be the last example of the lesson. In the numerator, we have y to the 1/2 plus 4 all over y to the 1/2 minus 1. What I recommend is to convert the y to the 1/2 to the square root of y. And then we'll be able to treat this problem similar to how we've done in earlier lessons. We now see that we have the need for a conjugate pair. So we now copy and paste the denominator. But in doing so, we change the sign. That's how we'll get the inner and outer products to subtract out to 0. And remove the radicals from the problem.